Every night, long before we had telescopes or complex equations, humans looked up at the sky and felt the same quiet pull. Stars moved slowly, predictably, yet they seemed completely unreachable. And somewhere in the back of the mind, a simple question started to form. Where does all of this end? Not what's inside the universe, or how it all works, but where it stops, if it stops at all. This question didn't come from science. It came from intuition. It came from living in a world where everything has edges. Even the oceans, as huge as they seem, eventually meet land. Our lives begin and end. Our days begin and end. So, it feels natural to assume the universe must also end somewhere, that space itself must eventually just run out. But this assumption, as we're about to discover, might be the most misleading intuition we have. To understand why this question is so persistent, we need to start not with the universe, but with ourselves. Human perception evolved in small spaces. We lived in forests, on plains, in caves, and along coastlines. We learned to navigate environments measured in meters and kilometers, not light years. Our brains got really good at understanding containers and their contents, inside and outside, here and there. This mental framework is perfect for survival, but it quietly breaks when we try to apply it to space itself. You see, space isn't an object sitting inside something larger. It's the stage on which all objects appear. Asking where space ends is fundamentally different from asking where a river or a road ends. And yet, our minds keep insisting on asking, because we just don't have another intuitive language to use. Ancient civilizations answered this question in ways that reflected their own lived experiences. To the Babylonians, the universe was a flat piece of land surrounded by cosmic waters, all capped by a solid dome. The stars were just stuck to that dome, fixed and eternal. Beyond it, chaos. To the Egyptians, the sky was a goddess arching over the world. For many early cultures, the universe wasn't infinite or abstract. It was structured, layered, and definitely finite. These models weren't foolish. They were careful interpretations of the evidence they had. The sky really does look like a dome. The stars really do seem fixed to a surface. Without instruments, math, or physics, these explanations were totally reasonable. The idea that space itself could be endless would have felt unnecessary, even absurd. Then, Greek thinkers started to refine these ideas. Aristotle imagined a universe of nested spheres, each one carrying a celestial body, with Earth right at the center. Beyond the outermost sphere of stars, Aristotle claimed, there was nothing. Not even empty space, but literally no existence at all. The concept of beyond just didn't apply. This idea dominated human thought for nearly 2,000 years because it fit perfectly with observation, philosophy, and theology. Everything had its place. Everything had a boundary. The universe was complete. And yet, even back in ancient Greece, cracks started to appear in this perfect model. A philosopher named Archytas posed a deceptively simple thought experiment. Imagine you travel to the absolute outer edge of the universe and you stick your hand out. If something blocks your hand, well, then that thing must be part of the universe, which means you haven't reached the true edge yet. But if nothing blocks your hand, then your hand is extending into space, which means space continues beyond the supposed boundary. Either way, the edge just dissolves. This paradox revealed something deeply unsettling. Our idea of an edge might not apply to space at all. For centuries, thinkers struggled with this. Medieval scholars debated whether nothingness could exist, whether God occupied the space beyond the stars, whether space itself was finite or infinite. But these were mostly philosophical debates. There was no way to actually test them. The universe remained distant, unreachable, and mysterious. Everything changed when humanity learned to look deeper. Telescopes shattered the illusion of a perfect, unchanging sky. Galileo saw mountains on the moon, spots on the sun, and moons orbiting Jupiter. The heavens were no longer divine and separate. They were physical places governed by laws. Newton took this even further, describing space as infinite and absolute, stretching endlessly in all directions. In Newton's universe, there was no center and no edge. Space was an infinite stage where matter moved around. This solved some problems, but it created new ones. For example, if space was infinite and filled with matter, why hadn't gravity just collapsed everything into one giant cosmic clump? Newton didn't have a good answer. As the centuries passed, astronomy became a science of measurement. We calculated distances. We placed stars in 3 dimensions. We discovered entire galaxies beyond our own Milky Way. The universe expanded in scale again and again, and each expansion just pushed the question further away. Where does the universe end? The answer was no longer just beyond the stars. The stars themselves were inside something far, far larger. Then came the most radical shift of all. Einstein showed that space and time weren't just fixed backgrounds. They were dynamic, flexible, and shaped by matter and energy. Space could curve, time could stretch. This meant the universe no longer needed an edge to be finite. Think about the surface of the Earth. It's finite. You can measure its area, but it has no boundary. You could travel on its surface forever and never hit a wall. In the same way, space itself could be finite, yet unbounded. You could travel in a straight line forever and never encounter an edge, eventually just ending up back where you started. This idea is deeply counterintuitive, because it contradicts everything our daily experience teaches us about limits. At the same time, our observations revealed something else incredible. The universe is expanding. Galaxies are moving away from each other, not because they're flying through space, but because space itself is stretching between them. This expansion introduced a new concept, the observable universe. There is a limit to how far we can see, not because space ends there, but because light has a finite speed and the universe has a finite age. Beyond a certain distance, light simply hasn't had enough time since the Big Bang to reach us yet. This creates a horizon, not a wall. It's a limit of our observation, not a limit of existence. This distinction is crucial and often misunderstood. The observable universe has an edge, but the universe itself may not. The horizon moves with us. No matter where you are in the cosmos, you are always at the center of your own observable universe. Asking what lies at the edge of the observable universe is like asking what lies at the horizon on the ocean. The horizon isn't a place you can actually reach. It's a limit that follows you wherever you go. And yet, even with this understanding, the question refuses to disappear. If the universe has no edge, if it goes on forever, what does forever even mean? Infinity isn't just a really big number. It's a fundamentally different concept. In an infinite universe, every possible configuration of matter has to occur somewhere. That means there are regions of space identical to ours, infinitely many of them, separated by unimaginable distances. This isn't science fiction. It's a direct, logical consequence of infinite space and a finite number of ways particles can be arranged. The implications are disturbing, fascinating, and deeply humbling. But perhaps the most important realization is this: the question, where does the universe end, might just be the wrong question to ask. It assumes that the universe is a thing contained inside something else. It assumes there's an outside. But if the universe is, by definition, everything that exists, there can be no outside. There's nothing for it to be inside of. The universe doesn't end the way objects end. It may end in time. It may end in change. It may end in our knowledge of it. But spatially, the idea of an edge may simply not apply. This realization doesn't make the universe less mysterious. It makes it more so. The absence of an edge challenges the deepest structures of our intuition. It forces us to accept that reality may not conform to the mental categories that evolved to help us survive. The universe doesn't owe us comfort. It doesn't owe us simplicity. It only offers patterns, laws, and limits that we can slowly, patiently uncover. As this series unfolds, we'll move carefully through these ideas. We'll explore what we mean by space, by boundaries, and by infinity. We'll examine what physics can tell us and where it currently falls silent. We will look at the beginning of the universe and its possible endings. We will confront horizons we cannot cross and questions we may never be able to answer. Not with urgency, but with calm. Not with fear, but with curiosity. The universe may not have an edge because edges belong to things inside space, not to space itself. And even if it has no final answer, the act of asking it connects you to every mind that has ever looked into the night sky and wondered. Thanks for joining me on this journey. When we talk about where the universe ends, the first thing we have to face is a quiet but unsettling truth. The universe doesn't behave like anything in our everyday experience. Every object you've ever touched has an edge. Every place you've ever been has a boundary. But the universe isn't an object inside something larger. It is everything's time, matter, and energy. So asking where it ends isn't like asking where a road ends. It's asking if existence itself has a limit. To understand this, we have to leave our intuition behind and follow the clues from observation and logic. The first clue comes from light. Everything we know about the distant cosmos comes from light, which travels incredibly fast, but not infinitely fast. The universe is also about 13.8 billion years old, which means light has only had that long to travel toward us. But here's the twist. While that light was traveling, space itself was expanding. This means the most distant things we can see today aren't 13.8 billion light-years away, but about 46.5 billion light-years away. This defines the boundary of our observable universe. It's a sphere centered on us, not because we're special, but because observation is always centered on the observer. An alien civilization in a distant galaxy would have its own observable universe. Seeing parts of the cosmos we can't, just as we see parts they can't. The edge of the observable universe isn't a physical wall. It's a horizon, a limit defined by time and light speed. It's like the horizon on the ocean. You can never reach it because it moves with you. If you could magically travel billions of light years, your observable universe would just recenter on your new position. But there's another, more permanent horizon. The expansion of the universe is accelerating, driven by something called dark energy. This means there are galaxies we can see today whose future light will never reach us. The space between us and them is expanding so fast that light can no longer win the race. Over eons, those galaxies will fade from our view, disappearing beyond a cosmic event horizon forever. This brings us to a mind-bending question. Is the universe as a whole finite or infinite? Does space go on forever, or does it curve back on itself? Think about the surface of the Earth. It's finite, but it has no edge. If you travel in a straight line, you eventually come back to where you started. The universe could be like that, a finite volume, with no boundaries, just curved in a way we can't perceive. Or it could be flat and extend infinitely in all directions. Our best measurements, from studying the faint afterglow of the Big Bang, suggest the universe is incredibly flat. In most theories, a flat universe is an infinite one. Now, we might just be seeing a small patch of a gigantic, curved universe that only looks flat to us, the same way the ground looks flat, even though we're on a sphere. So the most honest answer we have right now is that the universe is either infinite or so vast that for all practical purposes, it might as well be. In either case, there's no edge you could crash into. The idea of infinity is wild. If the universe is infinite and matter is spread out pretty evenly, then every possible arrangement of particles must exist somewhere. That means unimaginably far away. There's another Earth, with another version of you, living an identical life. And another you, where you made a different choice this morning. Every possibility is playing out somewhere in the infinite expanse. This isn't science fiction. It's a logical consequence of infinity. So, where does the universe end? It doesn't seem to end in space. There's no wall, no border, no final point. Instead, the universe has different kinds of endings. It has horizons, boundaries of what we can see and what we can ever know. It also has an end in time. The universe had a beginning in the Big Bang, and it's heading toward a future fate. Maybe a cold, empty heat death, where all stars have burned out and nothing happens anymore. Perhaps the most profound answer is that the edge of the universe is unseen, a place you can visit. It's the boundary of our own understanding. We're constantly pushing that boundary outward, but there will always be mysteries just beyond our reach. Thanks for watching. By now, one thing should feel increasingly clear. The universe refuses to behave like anything our minds evolved to understand. Every instinct you have tells you that things must end somewhere. Roads end, stories end, lives end. Even ideas feel incomplete without a conclusion. Yet the universe may be the one thing that truly has no spatial ending at all. This is not poetry or philosophy. It is the logical consequence of everything we have measured so far. If space is flat and infinite, it doesn't just taper off, thin out, or dissolve into nothingness. It simply continues forever. And forever here doesn't mean a very long distance. It means no distance at which continuation stops. No final coordinate, no last location, no cosmic edge waiting to be reached. To understand why this feels so disturbing, consider how deeply the idea of boundaries is wired into us. Our brains evolved on a planet where survival depended on knowing where things ended. Cliffs, rivers, forests, territories, boundaries mattered. Anything without a boundary feels incomplete, unsafe, or unreal. Infinity breaks this mental model completely. You can't visualize it. You can't walk to it. You can't stand at its edge, because an edge doesn't exist. Every attempt to imagine the end of an infinite universe quietly smuggles in another space beyond it, which immediately contradicts the idea of an end. The moment you imagine outside, you have already placed the universe inside something else, which it is not. This is why ancient cosmologies always included walls, domes, oceans, or spheres. A bounded universe felt natural. The sky as a dome, the stars embedded in a shell. Beyond that, either nothing or gods. These ideas made sense because they mirrored our human-scale experience. But modern physics stripped these metaphors away. There is no shell holding the stars. There is no cosmic ceiling. There is no place where space transitions into non-space. Space isn't a substance floating in something else. Space asterisk is asterisk the something else. Even the Big Bang doesn't give us an edge. It gives us a beginning in time, not a boundary in space. At the moment of the Big Bang, space didn't explode outward from a point into some pre-existing emptiness. Space itself came into existence everywhere at once. Every region of space today was compressed into an unimaginably hot, dense state. If the universe is infinite now, it was infinite then too, just scaled down. Infinity doesn't require growth. It only requires continuation without termination. This brings us to one of the strangest realizations in cosmology. The universe may have no center either. When we say the universe is expanding, we don't mean galaxies are flying away from a central point. Expansion happens everywhere. Every region of space stretches relative to every other region. From any galaxy, all other galaxies appear to be receding. This means no location is special. No location marks a middle. If there is no center and no edge, the universe has a structure unlike anything we encounter in daily life. At this point, many people ask a deceptively simple question. If the universe is infinite, why isn't the night sky infinitely bright? This is known as Olber's paradox, and it puzzled astronomers for centuries. In an infinite, static universe filled uniformly with stars, every line of sight should eventually end on a star. The sky should glow like the surface of the sun, but it doesn't. The sky is dark. The resolution of this paradox teaches us something essential. The universe is not static. It has a finite age. Light from distant stars has not had infinite time to reach us. Many stars that could exist infinitely far away have not yet contributed their light. The darkness of the night sky is direct evidence that the universe had a beginning and is evolving in time. Now think carefully about what this means. The universe can be infinite in space, but finite in time. These two ideas are not contradictory. Space can extend forever, even if time has only flowed for 13.8 billion years so far. Imagine a ruler that extends infinitely in both directions, but was only revealed gradually as time passed. At first, only a small segment is visible. As time goes on, more of it becomes accessible. Not because the ruler grows, but because information about it has time to reach you. This is similar to how the observable universe works. As cosmic time continues, something counterintuitive happens. Even though more time passes, the observable universe doesn't keep growing forever. Because expansion is accelerating, there is a limit to how much of the universe we will ever see. There are regions whose light will never reach us no matter how long the universe exists. This creates a permanent observational boundary. Not a wall, not an edge, but a horizon beyond which reality exists, but remains forever hidden. The universe doesn't end there. Our access to it does. This distinction matters deeply. It means the universe may be endlessly vast, while our experience of it becomes increasingly small. In the far future, observers in our galaxy will see a dark, empty sky with only local stars and galaxies remaining visible. They may conclude that the universe is small and static, unaware that countless galaxies exist beyond their horizon. Knowledge itself becomes bounded by cosmic expansion. The universe doesn't need to shrink to feel empty. It only needs to outrun information. Now, consider the possibility that space is not infinite, but finite and curved. Even then, there is no edge. A closed universe loops back on itself. Travel far enough in one direction and you return to where you started. This kind of universe is finite in volume but unbounded. No wall exists. No border marks the end. Asking where it ends is like asking where the surface of the earth ends. It doesn't. It wraps. So whether the universe is infinite or finite, one conclusion remains consistent. There is no spatial edge you could ever reach. No final boundary where existence stops. The universe avoids ending in space entirely. Instead, it ends in horizons, limits, and transformations. But there is another unsettling idea that follows naturally from infinity. If the universe is infinite and matter is distributed roughly uniformly, then every possible arrangement of matter must occur somewhere, not once, but infinitely many times. This includes arrangements identical to our own observable universe. Somewhere beyond our horizon, there are regions where the same galaxies formed, the same stars ignited, the same planets cooled, and the same histories unfolded. There are versions of Earth where everything up to this moment is exactly the same, not similar, identical. This is not poetic exaggeration. It is a mathematical consequence of infinity combined with finite configurations of matter. This idea stretches the concept of identity to its breaking point. If infinitely many copies of you exist, what does individuality mean? If every possible outcome occurs somewhere, what does chance mean? These are not questions physics answers easily. They sit at the boundary between science, mathematics, and philosophy. Infinity forces us to confront the limits of explanation itself. And then there is time. Even if space has no edge, time almost certainly does. The universe began. It will also end in a meaningful sense. Whether through heat death, a big rip, or some unknown transformation, change will eventually cease. Complexity will fade. Structure will dissolve. This is not a dramatic explosion or collapse. It's a quiet fading into equilibrium. The universe doesn't slam into an ending. It drifts into stillness. So when we ask where the universe ends, the most honest answer is this. It doesn't end where we expect it to. It doesn't end in space. It ends in accessibility. It ends in observation. It ends in time. And perhaps most profoundly, it ends at the boundary of what minds like ours can ever fully grasp. The universe may be infinite, but our understanding is not. If the universe began with the Big Bang, then what existed before it? This question feels natural, almost inevitable. Because our minds are built to think in sequences. One moment follows another. Every event has a cause. Every beginning must come after something else. But the universe doesn't always respect the way our intuition works. In fact, when it comes to the Big Bang, intuition might be the worst guide we have. Asking what came before isn't wrong, but it might be a question that reality itself doesn't allow us to answer in the way we expect. To understand why, we need to be precise about what the Big Bang actually was. Popular culture often describes it as a massive explosion, a violent event that happened at some location in space, sending matter flying outward into an empty void. This image is deeply misleading. The Big Bang wasn't an explosion asterisk in asterisk space. It was the expansion asterisk of asterisk space. Space itself came into existence in that moment, along with time, energy, and matter. There was no pre-existing emptiness waiting to be filled. There was no outside. The Big Bang wasn't something that happened somewhere. It happened everywhere, all at once. The equations of general relativity tell us that as we trace the expansion of the universe backward, everything gets hotter, denser, and closer together. Eventually, we reach a point where these quantities become infinite. This point is called a singularity. But a singularity isn't a physical object. It's a sign that our mathematical description has broken down. It tells us that the theory we're using, general relativity, can no longer describe reality accurately beyond that point. This distinction is critical. The Big Bang singularity doesn't necessarily represent a literal beginning of existence. It represents the boundary of our current theories. And at extremely small scales and high energies, quantum effects become dominant. Without a complete theory of quantum gravity, we can't reliably describe what happened at the very earliest moments. This is why physicists are cautious. When asked what existed before the Big Bang, the most honest scientific answer is, we don't know. Not because the answer is unknowable, but because our current theories are incomplete. However, this hasn't stopped scientists from proposing fascinating models that try to extend the story. One of the simplest ideas is that the Big Bang wasn't a beginning at all, but a transition. In this view, the universe existed in some form before the Big Bang and underwent a dramatic change that led to the expansion we see today. These ideas are speculative, but they're grounded in serious attempts to merge relativity with quantum mechanics. One such idea is the Big Bounce. In these models, the universe didn't begin from nothing. Instead, it existed in a prior, contracting phase. As the universe shrank, densities soared, but powerful quantum gravity effects kicked in and prevented a total collapse. Instead of crunching into an infinitely dense point, the universe reached a minimum size and then bounced, transitioning into the expansion we're in now. Loop quantum gravity is one theory that provides a framework for this. In this theory, space itself is made of tiny, discrete units. These quantum properties of space create a kind of repulsive force at extreme densities, preventing an infinite crush. When applied to cosmology, this leads naturally to a bounce. Before our expanding universe, there was a contracting one with its own history. Time didn't begin at the Big Bang. It passed right through it. If this is correct, then there was another universe phase before ours. But this just raises more questions. How long did that contracting phase last? Was it similar to our universe? And if a bounce can happen once, could it happen repeatedly? This leads to cyclic models, where the universe undergoes an endless series of expansions and contractions. Each cycle starts with a big bang-like event and ends with a bounce that triggers the next. The universe has no beginning and no end. It just oscillates forever. The brilliant physicist Roger Penrose proposed a more subtle version of this, called conformal cyclic cosmology. He suggests that the very, very remote future of one universe becomes mathematically identical to the Big Bang of the next. In the far future, after all matter has decayed and only radiation is left, the universe loses all sense of scale. Without mass, time and distance lose their meaning. Penrose argues this scale-free state can be reinterpreted as a new Big Bang, starting the next cosmic eon. These ideas are elegant, but they remain speculative. We don't have definitive proof for a bounce or a cyclic universe. The cosmic microwave background, the afterglow of the Big Bang might hold subtle clues. But right now, the data is inconclusive. Another approach comes from inflationary cosmology. Inflation proposes that the very early universe underwent a brief but mind-bogglingly rapid expansion. This idea successfully explains a lot of things we observe, like why the universe is so uniform and flat. But what caused inflation to start? In many models, inflation is driven by a quantum field. But quantum fields fluctuate. In some regions, inflation ends, creating a bubble universe like ours. In other regions, it keeps going. This leads to the idea of eternal inflation. Inflation never completely stops. It ends in pockets, creating new bubble universes, while the space between them keeps inflating. Our universe would be just one bubble in a vast, eternally inflating multiverse. In this picture, our Big Bang wasn't the beginning of everything, just the beginning of our local region. So what was before? The inflating background. Quantum cosmology pushes these questions even further. Some models suggest that time itself isn't fundamental. Instead, time emerges from the relationships between quantum states. In these models, asking what happened before the Big Bang is like asking what is north of the North Pole. The question assumes a direction that simply doesn't exist beyond a certain point. This idea is deeply counterintuitive, but it's supported by how time behaves in general relativity. Near the Big Bang, the distinction between space and time breaks down. The universe doesn't evolve in time the way we experience it. Instead, its entire history might exist as a single four-dimensional space-time structure. The universe doesn't come from something earlier. It's simply past, present, and future are all part of the same block. The Big Bang isn't a moment in time. It's a boundary of the geometry itself. This challenges our deepest assumption, causality. In our lives, causes always precede effects. But in a universe where time itself emerges, causality might only be a local rule. The universe may not need an external cause in the way events within it do. This leads to philosophical questions that science alone can't answer. Does the universe require a cause? If time began with the universe, is a cause even a meaningful concept? Physics doesn't have the final answers yet. What it does provide are models showing how the universe could exist without a traditional before. Once we accept that the universe had a beginning, an equally unsettling question follows naturally. Will it end? And if it does, what will that ending look like? Unlike ancient myths that imagined cosmic destruction as a dramatic event involving gods or fire, modern cosmology approaches this question quietly, patiently, using equations, observations, and deep time. The end of the universe, if it comes, will not be sudden or violent in any human sense. It will unfold over timescales so vast that ordinary language struggles to describe them. Yet the laws of physics give us clues, and those clues point toward a future that is both simple and profoundly strange. To understand how the universe might end, we need to understand what governs its large-scale behavior. The most important factor is expansion. Since Edwin Hubble's discovery in 1929, we've known that the universe is expanding, with galaxies moving away from one another as space itself stretches. But expansion alone does not determine the ultimate fate. What matters is how that expansion changes over time. Does it slow down, stop, reverse, or accelerate forever? The answer depends on the contents of the universe, particularly matter, radiation, and dark energy. For much of the 20th century, cosmologists assumed that gravity would eventually slow the expansion. Matter attracts matter. As galaxies move apart, their mutual gravitational pull should act like a brake. The question was whether there was enough matter to halt expansion entirely and cause a recollapse, or whether expansion would continue forever, gradually slowing but never stopping. These two possibilities were known as the Big Crunch and eternal expansion. Then, in 1998, everything changed. Two independent teams studying distant type Ia supernova made a shocking discovery. These exploding stars act as standard candles, allowing astronomers to measure cosmic distances with high precision. By comparing the brightness of nearby and distant supernova, researchers could infer how the expansion rate had changed over billions of years. They expected to find that expansion was slowing. Instead, they found the opposite. The expansion of the universe is accelerating. This acceleration implies the presence of a new component of the universe, one that counteracts gravity on large scales. We call it dark energy. Dark energy is not a substance we can touch or detect directly. We know it exists only through its gravitational effect on the expansion of space. It behaves unlike anything else in physics. It doesn't clump. It doesn't dilute as space expands. Instead, it appears to be an intrinsic property of space itself. Today, dark energy makes up about 68% of the total energy content of the universe. Dark matter contributes about 27%, and ordinary matter, the stuff you and I are made of, only about 5%. This balance determines the universe's fate. Because dark energy dominates, expansion is not slowing, it is speeding up. If dark energy remains constant over time, the universe will continue expanding forever, faster and faster. This leads to the scenario known as heat death, also called the Big Freeze. Despite the dramatic name, heat death is not a fiery catastrophe. It is a slow fading, a quiet extinguishing of structure and activity. To understand heat death, imagine the universe tens of billions of years from now. Galaxies outside our local group will gradually disappear from view as accelerated expansion carries them beyond our cosmic event horizon. Their light will never reach us, no matter how long we wait. The observable universe will shrink, not because space contracts, but because more and more regions become causally disconnected. Within our local group, gravity will keep galaxies bound together. The Milky Way and Andromeda will merge in about 4 billion years, forming a large elliptical galaxy. A few dozen nearby galaxies will remain gravitationally bound. Everything else will be lost to cosmic expansion. Star formation will continue for a time, but it will eventually slow and stop. Stars form from clouds of gas. As generations of stars live and die, they lock up gas in stellar remnants or eject it into intergalactic space. Over hundreds of billions of years, the supply of cold gas suitable for star formation will be exhausted. No new stars will form. Existing stars will burn out one by one. Red dwarfs, the smallest and longest-lived stars, will dominate the late universe. Some of them can burn for trillions of years, but even they are not eternal. Eventually, the last stars will fade into darkness, leaving behind white dwarfs, neutron stars, and black holes. As time stretches further, gravitational interactions will gradually dismantle galaxies. Close encounters between stars will eject many of them into interstellar space. Others will fall into black holes. Planets will be stripped from their stars, drifting alone through the darkness or spiraling into stellar remnants. On timescales of around 10 to the power of 40 years, even atomic matter may not survive. If protons are unstable, as some theories suggest, they will eventually decay. All ordinary matter will dissolve into radiation and subatomic particles. What remains will be an increasingly dilute soup of photons, neutrinos, electrons, and positrons. Black holes, often imagined as eternal, are not permanent either. In the 1970s, Stephen Hawking showed that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to lose mass and eventually evaporate. Small black holes evaporate quickly. Supermassive black holes take much longer, up to about 10 to the power of 100 years, but even they are finite. After the last black holes evaporate, the universe will be nearly empty. Space will continue expanding. The temperature will approach absolute zero. Energy will be spread so thinly that no meaningful processes can occur. Entropy will be maximized. This is heat death, not an end in the sense of destruction, but an end in the sense of change. Nothing interesting will ever happen again. Time, in a practical sense, will lose meaning. Without processes, without gradients, without change, there is nothing to mark the passage of moments. The universe will exist, but it will be static in every meaningful way. This is the most conservative prediction based on current observations. But it is not the only possibility. If dark energy is not constant, the future could be far stranger. Some models allow dark energy to increase over time. If its strength grows, expansion will accelerate more and more rapidly. Eventually, the expansion rate could overcome not just gravity, but all forces. This leads to the Big Rip scenario. In a Big Rip universe, galaxies are torn apart as expansion overwhelms gravitational binding. Later, star systems are ripped apart. Eventually, planets are pulled from their orbits. Finally, at the most extreme stage, even atoms and subatomic particles are torn apart as space itself expands faster than forces can hold matter together. The Big Rip would occur at a finite time in the future, perhaps tens of billions of years from now, depending on the behavior of dark energy. It would be sudden on cosmic timescales. Everything would be destroyed, not by heat or collision, but by the expansion of space itself. Current observations suggest that dark energy behaves like a cosmological constant, making the Big Rip unlikely. But we cannot rule it out completely. We are still learning what dark energy is. Another possibility is the Big Crunch. If dark energy weakens or reverses sign, expansion could slow, stop, and reverse. Gravity would take over. Galaxies would begin moving toward one another. The universe would contract, growing hotter and denser. Eventually, everything would collapse into a hydrogen state, perhaps similar to the Big Bang. In some models, a Big Crunch could lead to another bounce, starting a new expansion phase. In others, it would represent a true end. Current evidence does not favor this scenario. The expansion appears to be accelerating, not slowing, but cosmology has surprised us before. There are even more exotic possibilities. Vacuum decay could end the universe abruptly. Quantum field theory suggests that our universe may be in a metastable vacuum state, not the lowest possible energy configuration. If a lower energy vacuum exists, a transition could occur. A bubble of true vacuum would form and expand at the speed of light, altering the laws of physics within it. Atoms would not survive. Chemistry would cease. Everything would be erased without warning. The probability of such an event appears extremely low. Calculations suggest our vacuum is stable, 4 times far exceeding the current age of the universe. But the possibility exists. It represents an end, not through gradual fading or expansion, but through a sudden change in the rules of reality itself. Each of these endings reflects a different assumption about fundamental physics. Heat death assumes dark energy is constant. The Big Rip assumes it grows stronger. The Big Crunch assumes it weakens or reverses. Vacuum decay assumes our universe is not in its lowest energy state. What they share is a quiet inevitability. None of these endings involve intention or drama. They are consequences of physical laws playing out over deep time. The universe does not rush toward its end. It drifts. For human minds, this is difficult to accept. We are used to stories with climaxes, conclusions, and meaning. The universe offers none of these. It does not care whether it ends slowly or violently. It simply follows its equations. Yet there is something oddly calming about this. The universe does not rush. It does not panic. It unfolds. As the universe evolves toward these distant endings, what happens to information, to memory, and to the very idea of meaning itself? That's a story for next time. Thanks for watching, and don't forget to subscribe for more cosmic journeys. As we drift deeper into the far future of the universe, a quieter but more unsettling question begins to emerge. If everything ends, if stars burn out, galaxies dissolve, and even black holes evaporate, then does anything truly last forever? This question goes beyond astrophysics. It touches the very foundations of reality itself. Permanence, after all, is something the human mind instinctively searches for. We build monuments, write histories, preserve memories, and imagine legacies that endure. But the universe does not seem to share our attachment to permanence. On cosmic timescales, even the most stable structures dissolve. To understand whether anything lasts forever, we need to examine what physics allows to survive when time stretches toward infinity. The first thing to confront is entropy. Entropy is a measure of disorder, or, more precisely, a measure of how energy is distributed. The second law of thermodynamics tells us that in an isolated system, entropy tends to increase. The universe is the ultimate isolated system. From the moment of the Big Bang, entropy has been rising. Early in cosmic history, the universe was hot, dense, and relatively smooth. Over time, gravity caused matter to clump, forming stars and galaxies. At first glance, this seems like a decrease in entropy, but it is not. The formation of structures actually increases total entropy by releasing energy as heat and radiation. Every star that shines, every fusion reaction, every photon emitted contributes to the overall increase of entropy. As the universe ages, entropy continues its relentless rise. Stars convert nuclear fuel into radiation. Black holes grow by swallowing matter and radiation, becoming some of the highest entropy objects in existence. Eventually, when all usable energy gradients are exhausted, entropy reaches its maximum possible value. This is the state known as heat death. At that point, no process can extract work. Nothing can happen in any meaningful sense. If entropy always increases and reaches a maximum, then no physical structure can remain active forever. Even information, which we often imagine as abstract and eternal, is tied to physical systems. Information requires physical storage. Memory requires stable structures. When matter decays and energy disperses, information is erased. This raises a profound question. Is information itself conserved? For many years, physicists believed information could never be destroyed. This belief was challenged by black holes. According to classical general relativity, anything that falls into a black hole is lost forever, including all information about its state. This apparent destruction of information violated the core principles of quantum mechanics, leading to what's known as the black hole information paradox. After decades of debate, most physicists now believe that information is not truly destroyed, even by black holes. Instead, it is somehow encoded in subtle correlations in the Hawking radiation as the black hole evaporates. Information may be preserved in principle, but in practice, it becomes so scrambled and dispersed that it is effectively unrecoverable. Preservation in principle is not the same as persistence in any meaningful sense. If information exists only as microscopic correlations spread across the universe, inaccessible and unusable, can we really say it lasts? From a practical standpoint, it is gone. Even space-time itself may not be eternal. Some theories suggest that space-time is emergent, arising from more fundamental quantum relationships. If space-time is emergent, then it may not exist forever. It could dissolve or transform into something else as the universe evolves. Particles, too, are not necessarily permanent. Protons, once thought to be stable forever, may decay over extremely long timescales. Experiments have not yet observed proton decay, but many grand unified theories predict it. If protons decay, then all atomic matter will eventually disappear. Planets, stars, and even the remnants of black holes will not survive indefinitely. What about fundamental fields? Could they persist? Quantum fields permeate all of space. They define the properties of particles and forces. If the universe continues expanding forever, these fields will remain, but their excitations will diminish. The fields themselves may persist, but in a featureless, inactive state. Vacuum energy, associated with dark energy, might be the closest thing to something that lasts forever. If dark energy is truly a cosmological constant, It represents an energy density inherent to space itself. As long as space exists, dark energy exists. But even this does not guarantee permanence in a meaningful way. Dark energy doesn't create structure. It accelerates expansion, contributing to the dissolution of complexity. Some physicists have even proposed that the vacuum may not be eternal. A process called vacuum decay could occur, transforming space into a lower energy state with different physical laws. In that case, even the properties of empty space would not last forever. From this perspective, the universe appears fundamentally impermanent. Everything changes, everything fades. Nothing remains active indefinitely. This aligns with a deeper theme found across physics. Stability is often temporary. What appears eternal on human timescales is fleeting on cosmic ones. Yet, there is another way to think about permanence. While individual structures disappear, patterns may persist. The laws of physics themselves appear remarkably stable. The same equations that governed the early universe still govern it today. As far as we can tell, these laws do not change over time. If the laws of physics are eternal, then something does last forever. But even this is uncertain. Some theories suggest that physical laws could vary across different regions of a multiverse or change over cosmic epochs. What we observe as fixed may just be local and temporary. Mathematics, too, is often seen as eternal. Mathematical truths do not depend on the physical universe for their validity. The fact that 2 + 2 = 4 does not vanish when stars burn out. But whether mathematical existence counts as something lasting forever is a philosophical question, not a physical one. Another candidate for permanence is the total existence of reality itself. Even if the universe undergoes heat death, even if no processes occur, existence continues, space remains. Time may continue, even if nothing changes. In that sense, the universe lasts forever, even if it becomes empty and static. But does an unchanging universe meaningfully exist? If nothing happens, if no observer exists, if no information is processed, is existence meaningful? Physics does not answer this. It describes what happens, not what meaning is. Some cosmological models suggest that the universe never reaches a final, static state. The theory of eternal inflation implies that new universes are constantly forming. Even if our local universe reaches heat death, other regions continue evolving. In this broader picture, change never stops. Something is always happening somewhere. In the many worlds interpretation of quantum mechanics, reality branches endlessly. Even if individual branches fade, the branching process itself continues. There is no final state. Existence proliferates endlessly across a sea of quantum possibilities. And in cyclic cosmologies, universes are reborn. Heat death is not the end, but a transition. What appears permanent in one framework becomes temporary in another. These models offer a different kind of permanence, not the permanence of objects, but the permanence of process. Creation, transformation, and dissolution repeat endlessly. Nothing lasts, but something always happens. After confronting impermanence, entropy, and the slow fading of everything that exists, one question inevitably rises to the surface. If nothing lasts forever, if even the universe itself drifts toward silence, does any of it have meaning? This is not a scientific question in the narrow sense. No telescope can measure meaning. No equation can calculate purpose. Yet, it is a question that emerges naturally from everything cosmology tells us. The more clearly we see the universe as it truly is, vast, ancient, indifferent, the more urgently we ask whether our existence within it matters at all. For most of human history, meaning came from outside the physical universe. Ancient cultures imagined gods who created the cosmos with intention. The universe existed for a reason, and humanity had a role to play within a larger plan. Meaning was woven into the structure of reality itself. But modern cosmology stripped away these assumptions. The universe appears to operate according to impersonal laws. Stars form and die without intention. Galaxies collide without purpose. The expansion of space accelerates, not because it should, but because the equations say it must. There is no obvious sign that the universe cares whether we exist. This realization can feel deeply unsettling. If the universe has no built-in purpose, then perhaps meaning itself is an illusion. Perhaps our lives are nothing more than brief chemical reactions on a small planet in a vast, uncaring cosmos. This interpretation is tempting, especially when viewed through the cold lens of physics, but it may be incomplete. To understand why, we need to examine what we mean by meaning. Meaning is not a physical substance. It does not exist the way particles or forces do. Meaning arises from relationships, from experience, from interpretation. A rock has no meaning on its own. It becomes meaningful when a mind encounters it, names it, uses it, or remembers it. Meaning exists where awareness exists. The universe, by itself, may not have meaning. But within the universe, meaning emerges. It emerges wherever matter becomes complex enough to reflect on itself. Stars do not wonder why they shine. Galaxies do not ask where they are going. But conscious beings do. That fact alone changes the equation. From a purely physical perspective, consciousness is a process. Neurons firing, signals propagating, chemistry unfolding. But from the inside, consciousness is something else entirely. It is experience. It is awareness. It is the capacity to care. Meaning does not need to be written into the fabric of space-time to be real. It can arise locally, temporarily, wherever conditions allow. This does not make meaning fragile or fake. It makes it contextual. A sunset has meaning even though it will end. A conversation matters even though it will be forgotten. A life has value even though it is finite. Permanence is not a prerequisite for significance. Cosmology teaches us that the universe evolves. It changes. It produces structure, complexity, and eventually awareness. In the early universe, there were no atoms. Later, there were stars. Still later, there were planets. And eventually, on at least one planet, there were minds capable of asking questions about the universe itself. This sequence is not random noise. It is a story of increasing complexity, driven by simple laws. Some philosophers and scientists argue that this alone gives the universe a kind of meaning, not purpose in the sense of intention, but direction in the sense of emergence. The universe tends to produce complexity under the right conditions. It is not guaranteed. It is not universal, But when it happens, something new appears. Awareness appears. Reflection appears. Meaning appears. From this perspective, we are not meaningless accidents. We are natural outcomes of the universe's structure. The laws of physics allowed stars to form. Stars allowed planets to form. Planets allowed chemistry to become complex. Complex chemistry allowed life. Life allowed consciousness. Consciousness allowed meaning. This does not imply that the universe intended this outcome, but it does imply that meaning is a real phenomenon within the universe, not an illusion imposed from outside. Meaning exists because minds exist, and minds exist because the universe permits them. There is another, quieter way to think about cosmic meaning. The universe is vast beyond comprehension. Most of it will never know itself. Most regions will remain dark, empty, and silent. But in a few rare places, the universe becomes aware. Through us, the universe observes itself. It reflects on its own origins, structure, and fate. That is not nothing. Carl Sagan once said that we are a way for the cosmos to know itself. This is not poetry alone. It is a literal statement. Without observers, the universe contains events, but no stories. With observers, events become histories. Processes become explanations. Existence becomes something that can be contemplated. This does not make humans special in a cosmic hierarchy. We are not central, we are not chosen, we are not permanent, but we are rare in a meaningful way. Awareness is not common. It requires specific conditions, and wherever it arises, it creates meaning by its very nature. Of course, this meaning is local and temporary. Our species will not last forever. Our planet will not last forever. Even our galaxy will eventually fade. But temporary does not mean trivial. A song does not lose its beauty because it ends. A thought does not lose its truth because it is fleeting. In fact, impermanence may be what gives meaning its intensity. If time were infinite and nothing ever changed, nothing would matter. Choices would have no weight. Moments would have no urgency. It is precisely because existence is finite that meaning can exist at all. Cosmology does not strip life of meaning. It reframes it. Meaning is not handed down from the universe. It is created within it. It arises wherever conscious beings engage with reality, care about outcomes, remember the past, and imagine the future. This also means that meaning does not need cosmic validation. It does not need to last forever. It does not need to be recorded in the structure of space-time. It needs only to be experienced. Some people find this unsatisfying. They want meaning to be objective, eternal, guaranteed. But physics offers no such guarantee. What it offers instead is possibility. The possibility for meaning to arise, again and again, wherever conditions allow. There is also a darker implication. If meaning is local and emergent, it can also disappear. When minds vanish, so does meaning. A future universe filled only with cold particles and empty space would have no meaning, not because it is tragic, but because there would be no one to experience it. This is not a failure of the universe. It is simply how meaning works. Meaning is relational. It exists in the interaction between mind and world. Remove one, and meaning dissolves. This realization can lead to despair, but it can also lead to clarity. If meaning is not guaranteed by the universe, then it is something we participate in creating. Our actions matter because they affect experiences. they shape memories, they influence other minds. Cosmology tells us we are small. Philosophy reminds us that small does not mean insignificant. A single thought can carry meaning even in an infinite universe. A single moment of awareness can be complete even if it is surrounded by emptiness. The universe may not care whether we exist, but we care, and that caring is not an illusion. It is a real phenomenon produced by real processes in a real universe. Meaning does not need cosmic endorsement to be real. As we drift further into this exploration, one final question waits ahead. If meaning arises within the universe, and if the universe allows infinite possibilities, could there be other versions of reality where meaning unfolds differently? Other universes, other outcomes, other versions of existence. We'll explore that next time. Thanks for watching. Once we accept that meaning arises locally within our universe and not from some built-in cosmic purpose, a much stranger possibility opens up. What if our universe is not the only one? What if existence itself is far larger than even the observable cosmos? The idea of other universes sounds like science fiction, but it didn't originate there. It emerged naturally from serious attempts to understand the laws of physics at their deepest level. When physicists follow those laws to their logical conclusions, they repeatedly encounter the same unsettling implication. Reality may be far more expansive than a single universe. To be clear, the word multiverse doesn't refer to one specific theory. It's an umbrella term that covers several very different ideas. Some are conservative extensions of well-tested physics. Others are speculative consequences of theories not yet confirmed. What they all share is the suggestion that our universe is only one region within a much larger structure of reality. The simplest version of a multiverse doesn't require exotic new physics at all. It follows directly from the possibility that space is infinite. If the universe extends infinitely in all directions and matter is distributed roughly uniformly, then the observable universe represents only a tiny patch of a much larger whole. Beyond our cosmic horizon, there would simply be more galaxies, more stars, more planets, repeating endlessly. In such an infinite universe, every possible configuration of matter that doesn't violate physical laws must occur somewhere. Not once, but infinitely many times. This leads to a deeply unsettling implication. Somewhere unimaginably far away, beyond any possibility of contact, there may exist regions of space identical to our own observable universe. Entire galaxies arranged the same way, planets orbiting the same stars, even versions of Earth with people living lives indistinguishable from ours. Not similar, but identical, down to every single atom, and not just one such region, but infinitely many. This isn't speculation in the loose sense. It's a direct consequence of infinity combined with finite possibilities. The number of possible arrangements of matter within a finite volume is enormous, but it's still finite. If space is infinite, those arrangements are bound to repeat. Reality becomes a vast cosmic repetition. However, this version of the multiverse is still part of a single, continuous universe. All regions share the same physical laws. They are simply very, very far apart. More radical multiverse ideas go much further. One of the most influential comes from the theory of cosmic inflation. Inflation was originally proposed to explain why our universe appears so flat, uniform, and isotropic. But many inflationary models naturally lead to what's called eternal inflation. In these models, inflation doesn't end everywhere at once. Instead, it continues in some regions while ending in others. Where inflation ends, a bubble universe forms. Inside this bubble, inflation stops, and normal cosmic expansion begins. This looks like a big bang to any observers inside the bubble. But outside the bubble, inflation continues, stretching space at an exponential rate. New bubbles constantly form. Each bubble is its own universe, with its own space-time, its own history, and possibly its own physical properties. In eternal inflation, the multiverse grows without end. The space between the bubbles expands so rapidly that they can never collide in any meaningful way. Each universe is causally isolated from the others. No signal can ever travel from one bubble to another. For all practical purposes, they are separate realities. Our universe, in this picture, is just one bubble among countless others. The Big Bang wasn't the beginning of everything. It was simply the beginning of our local region. Beyond our cosmic horizon lies not empty space, but more inflating space and more universes. Eternal inflation also provides a possible explanation for the fine-tuning problem. If many universes exist with different physical properties, then it's not surprising that at least some of them would permit complex structures and life. We find ourselves in one of those universes simply because we couldn't exist in any other kind. This line of reasoning is known as the anthropic principle. Another multiverse idea emerges from string theory. String theory attempts to unify all fundamental forces by describing particles as tiny, vibrating strings in higher dimensional space. To be mathematically consistent, string theory requires extra dimensions beyond the familiar 3 of space and 1 of time. These extra dimensions must be compactified or curled up into extremely small shapes. The problem is, there are many, many ways to compactify these dimensions. Each configuration leads to different low-energy physics, different particle masses, different force strengths, different constants of nature. Calculations suggest there may be on the order of 10 to the power of 500 possible configurations. This enormous set of possibilities is called the string landscape. If eternal inflation is correct, different bubble universes could settle into different points on this landscape. Each bubble would have its own version of physics. Some universes would have no stable atoms, others would collapse instantly. Still others would expand too fast for any structure to form. Only a tiny fraction would permit complexity and life. Our universe would be one of the rare life-permitting regions in this vast landscape. And again, the anthropic principle explains why we observe what we do. We observe these laws because only these laws allow observers. Quantum mechanics offers yet another kind of multiverse. In the many worlds interpretation, every quantum event with multiple possible outcomes leads to a branching of reality. All outcomes occur, but in different branches. These branches don't interact after they split. Each branch is a complete universe with its own history. This quantum multiverse isn't spatially separated. The branches coexist mathematically, but are inaccessible to one another. Every decision, every measurement, every random decay event creates new branches. Over cosmic time, the number of branches becomes unimaginably large, possibly infinite. In some branches, civilizations flourish. In others, they never arise. In some, you made different choices. In others, Earth was destroyed by an asteroid. All possibilities consistent with quantum mechanics occur somewhere in the branching structure. This interpretation solves certain problems in quantum theory, but it also raises deep philosophical questions. What does probability even mean if all outcomes occur? What does identity mean if multiple versions of you exist? These questions remain unresolved. There's also a darker consequence shared by many multiverse theories. If reality is infinite and contains all possibilities, then extremely rare events become inevitable. This leads to paradoxes like Boltzmann brains, hypothetical, self-aware observers formed by random fluctuations rather than by evolutionary history. In an infinite universe, such observers might vastly outnumber ordinary ones, leading to disturbing conclusions about what we should expect to observe. These paradoxes suggest that infinity, when combined with probability, creates deep conceptual problems. Physicists call this the measure problem. In an infinite multiverse, how do you assign probabilities? If infinitely many universes have property A and infinitely many have property B, what does it mean to say one is more likely? Different ways of regulating infinity give different answers, and there's no agreed-upon solution. This casts doubt on our ability to make testable predictions in multiverse models. And this brings us to the most important question. Is the multiverse scientific? Science relies on testability. A theory must make predictions that can, at least in principle, be tested by observation. Most multiverse models place other universes forever beyond our cosmic horizon. We can never observe them directly. We can't interact with them. We can't receive signals from them. Some argue this makes the multiverse unscientific. Others argue that if the multiverse arises inevitably from well-tested theories like inflation or quantum mechanics, then it should be taken seriously, even if direct observation is impossible. After all, we accept many things we can't observe directly, like quarks or dark matter, because their effects are measurable. The difference is subtle. Quarks and dark matter influence observations within our universe. Other universes may not. The debate remains open. Yet, even if the multiverse cannot be tested directly, it reshapes how we think about reality. It challenges the assumption that our universe is unique. It suggests that the laws of physics we observe may not be fundamental necessities, but rather environmental conditions specific to our region of reality. This has profound implications for meaning. If countless universes exist, each with different properties, then existence itself is more like a vast landscape of possibilities than a single story. Meaning becomes local, not just within a universe, but within a particular branch or bubble. We are not the center of everything. We are not even the center of one universe. We are inhabitants of one region among possibly infinite regions. Yet, within this region, experience matters. Awareness matters. Meaning arises. The multiverse doesn't diminish our significance. It contextualizes it. We are significant to ourselves and to those we affect. And perhaps that is enough. In the next part, we will confront a deeply unsettling implication of infinite universes. If reality allows infinite versions of everything, what does that say about identity, uniqueness, and the very idea of a single self? Thanks for watching, and be sure to subscribe for more. Have you ever stared up at the night sky and felt a sense of awe, wondering what's out there? It's a feeling we all share. But what if I told you that somewhere in the endless expanse of reality, there might be another you looking up at their own sky, thinking the exact same thoughts. This isn't just a philosophical daydream. It's a very real possibility that arises from modern cosmology and quantum physics. Once we consider that the universe might be infinite, or that our universe is just one of countless others in a vast multiverse, a deeply personal question emerges. Are there infinite versions of you? I'm not talking about a metaphorical twin or a soulmate. I mean a literal, physical copy. Another person with your memories, your dreams, your exact genetic code, living out a life that might be identical to yours, or one that diverged just a moment ago. This idea can feel unsettling. It challenges our sense of identity. If you're not unique, then who are you really? What does it mean to be an individual in a cosmos that might be filled with infinite copies? To understand this, we need to be clear about what kind of infinity we're talking about. Let's start with a simple, spatially infinite universe. Imagine space just goes on forever, with the same laws of physics and the same kinds of matter everywhere. Now, think about our observable universe, the bubble of space we can see. The number of ways particles can be arranged within this bubble is absolutely enormous, but it's not infinite. There's a finite number of possible configurations. If you have a finite number of possibilities, but an infinite amount of space to play with, what happens? Repetition becomes inevitable. It's like having a limited deck of cards and an infinite number of shuffles. Eventually, you're guaranteed to get the same sequence of cards again. The same logic applies to the universe. This means that somewhere far, far beyond the edge of what we can see, there could be another region of space that is an exact atom-for-atom copy of our own. In that region, there would be a copy of the Milky Way, a copy of our solar system, a copy of Earth, and a copy of you, listening to these very words. And not just one copy infinitely, many of them, scattered throughout the infinite expanse. This staggering conclusion doesn't require any weird new physics. It's a direct consequence of combining two simple ideas, an infinite universe and random distribution. If these conditions are met, then your duplicates aren't just a possibility, they're a mathematical certainty. Now, before you start planning a family reunion, the distance to your nearest copy would be mind-bogglingly vast. The numbers are so large, they're almost meaningless. Something like 10 to the power of 10 to the power of 115 meters away. You could never travel there. You could never send a message. The constant expansion of space creates an uncrossable cosmic ocean between you and your doppelgangers. You are, and always will be, completely isolated from them. This brings up a profound question. If another version of you exists, but you can never meet them, are they really you? Our sense of self, our identity, is built on a continuous stream of consciousness. You are you because you remember your past and you anticipate your future. That continuity is a private, unbroken chain. Another you, even if they were identical a moment ago, does not share your experiences from this point forward. They are a separate person, living a separate life. So, in a way, duplication doesn't erase your individuality, it multiplies it. From the inside, each of you feels completely unique and singular. But space isn't the only place we find infinite copies. Quantum mechanics offers an even stranger, more intimate version of this idea through the many worlds interpretation. According to this theory, every time a quantum event has more than one possible outcome, the universe itself splits into multiple branches. Think of it like this. A radioactive atom can either decay or not decay. In the many worlds view, it does both. In one branch of reality, the atom decays, and in another, it doesn't. Both of these branches are equally real, and each one contains a version of you. This isn't happening just with atoms in a lab. It's happening constantly, everywhere. Even the tiny quantum processes firing in your brain could be causing reality to split. Over your lifetime, the number of these branches becomes astronomical. In each branch, a slightly different version of your life unfolds. There are branches where you made different choices, where you took that job or didn't. Branches where random events played out differently. In some, your life might be almost identical, while in others, a single small change led to a completely different destiny. Unlike the spatial copies, these quantum branches aren't far away in space. They coexist with us in a higher dimensional reality described by the quantum wave function. But just like their cosmic cousins, they are completely separate. Once a split occurs, the branches can never interact or communicate again. This idea messes with our intuition. If every possible outcome happens, what does it mean to say something is probable? What's the point of regretting a decision if another version of you made the opposite choice and is living with those consequences? Many worlds is mathematically elegant, but it forces us to rethink everything we thought we knew about choice, chance, and who we are. So, with all these potential copies floating around in space or branching off in quantum reality, you might start to feel a little insignificant. Does any of it matter? Here's the thing. Even if infinite versions of you exist, you will only ever experience one life, this one. You'll never meet your cosmic twins. You'll never get a report from your quantum counterparts. From your perspective, your life is singular and unique. Your uniqueness doesn't come from being the only one in the entire cosmos. It comes from your point of view. No one else has your exact continuity of memory and awareness. This can be a bit overwhelming. The thought that every possible version of your life is being played out somewhere. There are versions of you that achieve unimaginable success, and versions that face utter failure. Versions that lived long, happy lives, and versions that tragically did not. But this can also be strangely liberating. If every path is taken somewhere, it means the universe isn't keeping score. There's no single correct path. Your choices matter profoundly, but they matter here, in this reality. They shape the life you experience and the lives of those around you. The existence of other stories doesn't make your story any less meaningful. A beautiful melody doesn't lose its power just because other melodies exist. Some worry that if everything happens, then nothing matters. But that's confusing cosmic scale with personal significance. Pain is still painful, and joy is still joyful, regardless of what's happening trillions of light years away, or in another quantum branch. Your experience is what's real to you. There's a gentle humility in this idea. You are not the center of the universe, but you are the absolute center of your own experience. The cosmos may be vast, repetitive, and indifferent, but your awareness is local. It exists right here, right now, in this moment. And for you, this moment only happens once. That's more than enough to give it weight and meaning. Of course, we must remember that these are still theories. The idea of infinite versions of you depends on big assumptions we can't yet prove, like whether the universe is truly infinite, or if the many worlds interpretation is correct. It's possible that the universe is finite, and there are no exact duplicates at all. What we can say for sure is that the universe does seem to prioritize our need to feel special on a cosmic scale. but it absolutely guarantees your uniqueness on an experiential scale. Identity is defined by the continuous story you live, not by being a one-of-a-kind model in the cosmic warehouse. So, the next time you look up at the stars, remember this: you are part of a story that might be playing out in infinite variations across reality. But this version, the one you are living right now, is the only one you will ever know, and that makes it infinitely precious. Thanks for joining me on this journey through the cosmos and the self. If you enjoyed this, be sure to like and subscribe for more explorations into the biggest questions in the universe. See you next time. Once we accept the possibility of an infinite universe, a deeply personal question emerges. If reality repeats itself endlessly, does that mean there are infinite versions of you? Not metaphorically, literally, other versions of your life, unfolding somewhere else, maybe following the exact same path up to this very moment, or maybe diverging in small or dramatic ways. This idea can feel unsettling because it hits at the very core of our identity. Who are you, really, if you're not unique? What does individuality even mean in a universe that might contain infinite copies of you? To tackle this, we need to be clear about what kind of infinity we're talking about. Let's start with a spatially infinite universe, one that goes on forever in every direction, but with the same laws of physics everywhere. In this scenario, the argument for duplicates is all about simple probability. Think about our observable universe, the part we can see. Within this finite region, matter can only arrange itself in a huge but still finite number of ways. It's an unimaginably large number, but it's not infinite. Now, if space extends infinitely, and matter is spread out more or less evenly, then every possible arrangement must repeat itself eventually. Given infinite room and a finite number of combinations, repetition is not just possible, it's inevitable. This means that somewhere, far, far beyond our cosmic horizon, there could be a region of space that is an exact particle-for-particle copy of our own. In that region, there would be a planet identical to Earth, orbiting a star identical to our sun, with a person identical to you, listening to these very words at this exact moment. The distance to your nearest copy would be mind-boggling. Estimates put it at something like 10 to the power of 10 to the power of 115 meters away. You could never get there. No signal could ever travel between you and your other selves. This brings up a deep question. If another version of you exists, living the same life, is that person actually you? Or are they someone else entirely? You are you because you remember your past and you look forward to your future. That continuous thread of experience only exists for you within your own causal chain. As soon as your histories diverge, even slightly, your identities diverge too. They don't share your awareness or your experiences. They are separate minds. From the inside, each of you feels unique and singular. So, duplication doesn't erase your individuality. It multiplies it. Quantum mechanics throws an even stranger twist into this whole idea with the many worlds interpretation. In one branch, one outcome happens. In another branch, a different outcome happens. And both branches are equally real, each containing a version of you. The decay of a single atom, a photon hitting a sensor, maybe even some processes inside our own brains. Over time, the number of these branches becomes astronomical. In each branch, there's a version of you experiencing a different sequence of events. In some, you made different choices. In others, the world around you turned out differently. In some, you might not exist at all. And in others, your life might have followed an almost identical path until one tiny, random event changed everything. They exist within the mathematical fabric of reality itself. And just like your distant spatial copies, they can't communicate or interact with each other after they split. Each branch is its own complete reality from the perspective of the people living in it. This idea messes with our intuitions about probability and responsibility. If all outcomes happen, what does it mean to say something is likely? What does it mean to regret a choice if another version of you made the other one? It's a mathematically elegant theory, but it's a real mind-bender for our sense of identity and free will. There's a philosophical limit to how much any of this really matters to your daily life. Even if there are infinite versions of you out there, you will never meet them. You'll never swap stories or share memories. From your perspective, your life remains singular. The existence of duplicates does unchange the fact that this is the only life you will ever get to experience. In that sense, your uniqueness isn't about being the only one in the entire cosmos. It's about your perspective. You are unique because no one else sees the universe exactly as you do. From this point of view, with this specific continuity of memory and awareness, now there's another implication that can feel even more unsettling. Versions where you fail spectacularly. Versions where you never even made it to adulthood. Versions where history went a different way and you were never even born. Every single possibility is realized. This can feel overwhelming, but it can also be strangely freeing. If every outcome happens somewhere, then the universe isn't judging which one is the right one. There's no cosmic scorekeeper. Your choices matter to you, locally. A single story doesn't lose its meaning because other stories are being told. Some people worry that this idea of infinite duplication makes life meaningless. If everything happens, then nothing matters, right? But that's mixing up scale with significance. Meaning doesn't come from being rare across the cosmos. It comes from the impact you have within your own experience. Pain still hurts, even if it's happening infinitely many times elsewhere. Joy is still wonderful, even if it isn't unique to you. There's something really humbling in this idea. You are not the center of the universe, but you are the center of your experience. The universe might be vast and repetitive, but your awareness is always here, now, in this moment. Even in an infinite multiverse, this specific moment only happens once for you. And that's enough to give it weight. Of course, there's a deeper mystery here. If the universe does contain infinite copies, are they truly identical? Quantum uncertainty guarantees tiny, microscopic differences, and over time, those small differences would grow, causing the paths to diverge. And what if the universe is finite after all? Or if the period of cosmic inflation that made it so big wasn't eternal? After confronting the idea of infinite universes and infinite versions of ourselves, a deeper, more technical question quietly emerges. If reality truly involves infinity, does that break physics itself? Physics, after all, is built on prediction. It relies on probabilities, measurements, and equations that assume limits. Infinity challenges all of these assumptions at once. When quantities become infinite, calculations fail, probabilities lose meaning, and our intuition collapses. To understand whether infinity breaks physics, we have to look at how it shows up in our theories and what it really represents. In our everyday experience, infinity doesn't exist. We never encounter infinite objects, infinite energy, or infinite time. Everything around us is finite. Because of this, physics was developed as a science of finite systems. We measure finite distances, finite masses, and finite energies. Infinity enters physics not as something we measure, but as a signal. It usually tells us that a theory has reached its limit. This is most obvious when we talk about singularities. In general relativity, black holes are thought to contain singularities where density becomes infinite and space-time curvature blows up. Instead, they're understood as breakdowns of the theory. General relativity can't describe what happens at these extremes because it ignores quantum effects. So, in this context, infinity isn't a feature of reality, it's a warning sign. Quantum field theory also struggles with infinity. When physicists try to calculate the energy of empty space or the interactions between particles, their first attempts often produce infinite results. These infinities are handled through a process called renormalization, where the infinite quantities are systematically cancelled out or absorbed into things we can actually measure. Renormalization works incredibly well, producing predictions that match experiments with astonishing precision. But its success hides a deeper discomfort. Infinity appears. It gets removed by a mathematical procedure, and physics just carries on. Whether these infinities reflect something real or just show that our theory is incomplete remains an open question. Cosmology introduces infinity in a different way. If space is infinite, then the total amount of matter, energy, and everything else is also infinite. This immediately creates problems. How do you define probabilities in an infinite system? If infinitely many observers see outcome A and infinitely many see outcome B, what does it mean to say one is more likely? Infinity divided by infinity is undefined. This is known as the measure problem, and it's one of the most serious unresolved issues in modern cosmology. In an infinite universe or multiverse, predictions depend entirely on how you decide to count or regulate that infinity. Different methods of counting lead to different results. There's no single, agreed-upon way to assign probabilities in infinite spaces. For example, imagine there are infinitely many universes where a certain constant has value x and infinitely many where it has value y without a proper measure. You can't say whether x or y is more common. You can try to define a ratio, but the result depends on how you count. Change the order you count in, and the ratio changes. This isn't just a technical detail. It undermines the predictive power of the entire theory. Some physicists see this as proof that infinity isn't physically real. They argue that the universe must be finite in some fundamental way, even if it looks infinite on large scales. Others believe we just need new mathematical tools that can handle infinite sets consistently. The debate is far from over. Infinity also challenges causality. In a finite universe, events are connected by chains of cause and effect. But in an infinite universe, there could be infinitely many identical events happening independently. Causality becomes a local phenomenon, not a global one. The universe as a whole doesn't have a single, coherent history. It becomes a collection of disconnected stories. This doesn't break physics locally. The laws still work perfectly fine within any finite region. But it challenges the idea that physics can describe the entire universe as one single system. Instead, physics becomes a description of patches, not of the whole. Quantum mechanics adds another layer of difficulty. In the many worlds interpretation, the number of branches of reality grows without end. Each branch represents a possible history, and the total wave function contains infinitely many components. Probabilities are assigned based on amplitudes, not by counting branches. But why these amplitudes correspond to the probabilities we experience is one of the deepest puzzles in quantum physics. If all outcomes happen somewhere, what does probability even mean? Why should we expect to find ourselves in a world with a higher quantum weight rather than a rarer one? Many worlds provides no universally accepted answer. Infinity just makes the interpretation even more complicated. Then there's the Boltzmann brain problem, which pops up in infinite or extremely long-lived universes. In a universe that lasts forever or has infinite volume, random fluctuations will eventually produce any possible configuration of matter. That includes conscious brains that just spontaneously pop into existence from chaos. These Boltzmann brains would vastly outnumber ordinary observers like us who were formed through evolution. If this is true, then statistically you should expect to be a Boltzmann brain, not a normal human with a consistent history. Since you clearly experience a coherent world with consistent laws, something must be wrong with this line of reasoning. Either the universe isn't infinite in the way we think, or our use of probability is flawed. This paradox points to the same conclusion. Infinity breaks our usual way of reasoning. Our tools for counting, predicting, and explaining things fail when infinities get involved. Some physicists respond by adopting a pragmatic view. They argue that physics only needs to describe what's observable. From this perspective, whether the universe is truly infinite or just finite, but very large beyond our observable horizon, might be a meaningless question. Others strongly disagree. They argue that a true theory of everything must describe reality as it is, not just the part we can see. There's a deeper philosophical issue here. Physics assumes the universe can be described by mathematical structures, and mathematics handles infinity very well in certain contexts. But physical reality might not correspond perfectly to mathematical infinity. Just because a mathematical model allows for infinite solutions doesn't mean nature has to realize them. For example, the set of real numbers is infinite and continuous, but space itself might be quantized at the tiniest Planck scale. If space-time is discrete, then infinite continuity is just a useful approximation, not a fundamental feature. Similarly, the appearance of infinite volume might just come from stretching our equations beyond the domain where they re-valid. Infinity might be a useful abstraction, not a literal property of reality. So, does infinity break physics? The honest answer is that it exposes the limits of physics. Our theories work extraordinarily well within finite domains. They predict experiments with stunning accuracy. But when we extend them to infinity, they run into paradoxes, ambiguities, and unresolved questions. This doesn't mean physics is broken. It means physics is incomplete. Infinity isn't an enemy of science, but a reminder of its boundaries. From a calm, reflective perspective, this isn't a failure. It's an invitation. The universe might be structured in ways that require new concepts, new mathematics, and new ways of thinking. For now, physics remains a tool for understanding what we can observe and test. Beyond that lies speculation, philosophy, and wonder. The edge of infinity is also the edge of our knowledge. In the next part, we'll step back from the equations and paradoxes and ask a quieter question. Given everything we know, what is the universe ultimately like to experience from within? Not mathematically, but existentially. Thanks for watching, and don't forget to subscribe for more. After exploring infinity through equations, paradoxes, and abstract reasoning, It's time to pause and ask a more intimate question. What does it actually feel like to exist inside an infinite universe? Not what infinity means mathematically, not how it behaves physically, but how it's experienced from within a single conscious perspective. Because no matter how vast reality might be, every experience of it happens locally, inside one mind, at one moment in time. You wake up in a room, not in a multiverse. You move through streets, not through space-time diagrams. The sky feels large, but not endless. The stars look distant, but not incomprehensible. For us, infinity exists as an idea, not as a sensation. This difference between intellectual understanding and lived experience is crucial. We can know that the universe is vast, but we can't feel that vastness directly. Our senses are tuned to meters, seconds, and kilograms, not light years, eons, or cosmic horizons. When confronted with infinity, the mind does something protective. It compresses, it abstracts. Infinity becomes a symbol rather than a reality. This is why thinking about infinite space can feel strangely calm rather than terrifying. The mind never fully grasps it, so it can't completely overwhelm us. Yet, infinity still exerts a subtle emotional pressure. It changes how we locate ourselves. In a small, finite universe, every location might feel special. But in an infinite one, no location is privileged. There is no center, no edge, no unique vantage point. Every observer is local, and every perspective is partial. This realization can dissolve a sense of cosmic importance, but it can also dissolve cosmic loneliness. If there's no center, then being off-center isn't a failure. It's the default state for everyone. Living in an infinite universe also changes how we think about time. In everyday life, time feels scarce. Days pass quickly. Years feel short. Mortality quietly presses in. But against infinity, a human lifespan isn't just brief, it's vanishingly small. This can feel nihilistic at first. How can something so brief matter in an endless cosmos? But the feeling shifts when we remember that experience isn't measured in duration alone. A moment of awareness doesn't need to last forever to be complete. From within our own experience, infinity just disappears. Consciousness always exists right now. It doesn't stretch across eternity. It occupies the present. Whether the universe lasts forever or ends tomorrow does unchange the structure of your experience in this moment. Awareness doesn't feel shorter just because the universe is longer. There's also a strange comfort in knowing that the universe isn't watching. In a finite, purpose-driven cosmos, your actions might feel judged by something larger. Meaning isn't assigned to you. It's something you live. Existing in an infinite universe also reframes solitude. You might feel small, but you're not isolated in a cosmic sense. If the universe is truly infinite, then existence is abundant. You are not an exception in a barren void. You're part of a pattern that arises wherever conditions allow. Life may be rare locally, but it's not unique globally. This doesn't diminish your individuality. It just contextualizes it. At the same time, Infinity makes contact feel impossible. Even if other minds exist elsewhere, the distances are so vast that interaction is incredibly unlikely. The sky remains silent. This silence can feel profound. It suggests that existence is something we do largely alone, together only with those nearby in space and time. There's a subtle psychological effect here. Knowing that the universe is infinite doesn't make life feel bigger. It makes it feel more focused. What matters is what's near, what can be touched, what can be remembered. Infinity pushes meaning inward rather than outward. From a sleep-focused perspective, this realization is deeply calming. The universe doesn't demand anything from you. It doesn't require you to be significant on a cosmic scale. It doesn't expect you to leave a permanent mark. You're allowed to exist briefly, experience quietly, and disappear without consequence to the whole. This doesn't mean your experiences are meaningless. It means they're self-contained. They are like a dream that matters while it lasts, even if it fades completely afterward. There's also a gentle humility that comes from living in an infinite universe. You're not responsible for everything. You're not meant to understand everything. The universe is larger than comprehension, and that's not a personal failure. It's simply the nature of reality. When people first learn about infinity, they often feel a loss of control. If everything exists somewhere, if every outcome happens, then what's the point of choice? But from inside our own experience, choice still matters. Our decisions shape local outcomes. They affect real people. They alter real futures. Infinity doesn't erase causality at the human scale. It only dilutes it at the cosmic one. Existing in an infinite universe also changes how we think about endings. If the universe has no edge in space, and perhaps no final end in time, then endings become local events. Civilizations end, species end, stars end. But existence continues elsewhere. Endings lose their absolute quality. They become transitions rather than conclusions. This can soften the fear of finality. Death still matters. Loss still hurts. But the universe doesn't collapse when something ends. It continues unfolding in other places, other times. You are not holding reality together. You are participating in it. There's a quiet beauty in this perspective. The universe isn't a story with a single plot. It's a vast field of unfolding processes. Your life is one of them. Thanks for watching. At some point in every honest exploration of the universe, we arrive not at an answer, but at a boundary. not a physical edge in space, but a conceptual one, a line beyond which questions no longer produce testable answers. This is the limit of what we can ever know, and understanding this limit is just as important as understanding stars, galaxies, or the Big Bang itself. Science often feels like an endless expansion of knowledge. Telescopes get stronger, equations grow more precise, data sets become larger. From this perspective, it's tempting to believe that given enough time and technology, every mystery will eventually be solved. But this belief quietly assumes that reality is fully accessible to observation and measurement. Modern physics suggests otherwise. Some limits are practical. We can't build a telescope the size of the observable universe. We can't rewind cosmic time. We can't travel faster than light. These are technological constraints, but deeper than these are fundamental limits, boundaries imposed by the structure of reality itself. One such limit is the cosmic horizon. Because light travels at a finite speed and the universe has a finite age, there are regions of space whose light will never reach us. Not now, not in 1 trillion years. These regions aren't hidden by distance alone, but by causality. No signal from beyond the cosmic event horizon can ever influence us. This means that vast portions of the universe, perhaps infinite portions, are permanently inaccessible. Their existence can be inferred, but never observed. This is not a temporary limitation. No future technology can overcome it. Even if humanity survives for trillions of years, even if intelligence spreads across galaxies, the horizon remains. Space expands too quickly. The boundary moves faster than we ever could. This creates a permanent limit on observational knowledge. Another boundary comes from quantum mechanics. At the smallest scales, uncertainty is not a flaw in measurement. It's built into reality. Heisenberg's uncertainty principle tells us that certain pairs of properties, like position and momentum, cannot both be known with arbitrary precision. This isn't because our instruments are inadequate, but because the universe itself doesn't permit exact values for both simultaneously. This means there are facts about the world that are fundamentally indeterminate until measured. And in some interpretations, even measurement doesn't reveal a pre-existing value. It creates one. This blurs the line between knowing and being. The universe at its core may not be fully defined until interaction occurs. Then there is the limit imposed by chaos. Even in classical systems governed by deterministic laws, prediction breaks down. Small uncertainties in initial conditions grow exponentially over time. This is known as sensitive dependence on initial conditions. Weather is the most familiar example. In principle, the equations governing atmospheric motion are known. In practice, long-term prediction is impossible because we can never measure initial conditions with infinite precision. On cosmic scales, similar chaos applies. The exact future configuration of galaxies, stars, and planetary systems cannot be predicted indefinitely, not because the laws are unknown, but because small uncertainties amplify over time. Determinism does not guarantee predictability. Another profound limit arises from computation itself. The universe can be thought of as performing calculations as it evolves. But there are limits to computation. Certain problems are undecidable. Alan Turing showed that there are well-defined questions that no algorithm can ever answer. This isn't a matter of speed or memory. It's a fundamental limitation of logic. If the universe is governed by computable laws, then there are aspects of its behavior that are, in principle, unpredictable. No simulation, no matter how powerful, could compute them. Reality may contain questions that cannot be answered even by reality itself in a computational sense. Then there is the limit of explanation. Physics seeks to explain phenomena by reducing them to underlying laws. But at some point, explanation bottoms out. Why do the laws have the form they do? Why these constants? Why this structure rather than another? At present, these questions have no answers within physics. They may never have answers. Some propose a multiverse to explain fine-tuning. Others seek a deeper theory that uniquely determines all constants. But it's possible that the laws of physics are brute facts. They simply are. Explanation ends, not because of ignorance, but because there is nothing deeper to explain them with. There is also a limit imposed by perspective. All observation happens from within the universe. We can't step outside reality to view it from the outside. We can't compare our universe to alternatives in a controlled way. We can't rerun cosmic history with different initial conditions. We observe one universe from one vantage point. This makes certain questions inherently untestable. Why is there something rather than nothing? Why does existence exist? These are meaningful questions, but they may lie permanently beyond empirical science. They're not wrong questions. They are just not scientific ones. Another subtle limit arises from consciousness itself. All knowledge is filtered through experience. Even our most abstract theories are understood by minds evolved for survival, not for cosmic truth. Our intuitions are shaped by environments vastly smaller and slower than the universe. When we reason about infinity, quantum fields, or curved space-time, we rely on mathematical structures that extend far beyond intuition. Understanding becomes symbolic rather than experiential. This doesn't make knowledge false, but it means that complete comprehension may be impossible. We can manipulate equations correctly without ever fully grasping what they describe. Reality may be intelligible without being imaginable. There is also the limit of language. Words evolved to describe everyday objects and actions. They struggle with phenomena that have no direct analog in experience. Terms like nothing, before time, or outside the universe carry hidden assumptions that break down under scrutiny. Language can mislead even when used carefully. Even mathematics, the most precise language we have, has limits. Gödel's incompleteness theorems show that in any sufficiently powerful formal system, there are true statements that cannot be proven within the system. If the universe is describable by mathematics, then there may be truths about it that cannot be derived from its own formal description. This creates a humbling picture. Not only is the universe vast beyond imagination, but our access to its truth is fundamentally partial. There are things we will never see, facts we will never determine, explanations we will never complete. Yet this does not make science futile. It gives it shape. Knowing where knowledge ends helps us understand where meaning begins. Science tells us what is. It doesn't tell us how to feel about it. It doesn't tell us how to live. The limits of knowledge are not walls that trap us. They are horizons that define the space of inquiry. Within those horizons, understanding grows. Beyond them, mystery remains. And mystery is not failure. It's not ignorance waiting to be corrected. It's an intrinsic feature of existence. A universe that could be fully known might be simpler, but it would also be smaller. The fact that reality exceeds comprehension is part of what makes it profound. From a sleep-oriented perspective, this realization is deeply soothing. You are not expected to understand everything. You are not meant to resolve every question. The universe does not demand comprehension as a condition for belonging. You exist whether or not you understand why. In this sense, the limits of knowledge are a form of permission. Permission to rest. Permission to let unanswered questions remain unanswered. Permission to experience without explanation. As we approach the final part of this series, we will turn to the most personal question of all. Given everything we know and everything we cannot know, how should a finite mind live inside an infinite and mysterious universe? Thanks for watching. In those quiet moments of contemplating the universe, a simple misunderstanding often takes root. This feeling makes sense. We're wired to compare. Bigger seems stronger, older seems wiser, and larger seems more real. Scale isn't a measure of significance, and duration isn't a measure of meaning. Yes, the universe is vast. It contains distances so immense that light itself takes billions of years to cross them, and timescales so long that all of human history is just a flicker. But none of this automatically diminishes what happens within it. A thought doesn't become less real just because it exists inside a small brain. A decision isn't trivial just because it affects a tiny corner of space. Significance isn't spread out evenly across the cosmos. It concentrates wherever awareness exists. Think about it. A single conscious moment contains something the rest of the universe largely does not experience. Most of the universe is silent, cold, dark, and unaware. It follows physical laws without reflection. It doesn't notice itself. It requires the most delicate conditions. Stable stars, heavy elements formed in stellar explosions, long periods of cosmic calm, biological evolution, and intricate neural networks. The very fact that awareness can exist at all is extraordinary against the backdrop of an empty, unfeeling cosmos. So, when people say we're insignificant because the universe is large, they're confusing quantity with quality. A grain of sand is tiny compared to a mountain, but the mountain doesn't feel the wind. The grain does. That neuron, however, participates in thought. Significance emerges where patterns become meaningful to themselves. This self-referential loop changes everything. Awareness is the process that turns inert matter into living experience, and experience is the only place where meaning can ever appear. The universe doesn't hand us meaning, it simply permits it, and that permission is everything. There's another common misconception, that for something to be important, it has to be universally important. That if it doesn't matter everywhere, it doesn't matter anywhere. But that's simply not true. Meaning is local by its very nature. Pain matters profoundly to the one who feels it. Love matters deeply to the ones who share it. Understanding matters to the one who seeks it. Reality itself is built from local interactions that accumulate into the grand structures we see. Meaning follows the same rule. It starts locally, and it doesn't need a cosmic stamp of approval to be real. Now, let's consider time. A human life is short, a brief century at best. Compared to the age of the universe, it's just a blink. But we don't experience time on a cosmic scale. A second doesn't feel less real just because it's short. A moment of fear isn't diminished because it passes quickly. The duration of an experience affects our memory of it, not its intensity in the moment it happens. In fact, the finiteness of life is what intensifies meaning. If our moments were endless, there would be no urgency. Our choices would lose their weight. Commitments would dissolve. Scarcity is what sharpens our attention and focus. Knowing that our time is limited forces us to prioritize. It creates stakes. Without an ending, stories wouldn't exist. They would just be an endless middle, never reaching a resolution. The universe may go on for trillions of years, fading into heat death or cycling into a new creation. But within that vast, unfolding drama, individual lives create their own narratives. And these narratives are not illusions. There's another layer to this idea of smallness that we often miss. Small systems can have a disproportionately large impact on larger ones. A microscopic mutation can alter the course of an entire species. A single idea can reshape civilizations. A tiny error in the early conditions of the universe could have prevented galaxies from ever forming. Small causes can have enormous effects. Our actions exist within this very framework. And here's a subtle reversal worth considering. The universe may be large, but our perspective isn't external to it. We aren't observers looking in from the outside. Every measurement we take, every equation we write, every image from a telescope is just matter examining other matter. From this viewpoint, our smallness becomes a feature, not a defect. Only systems of a limited scale can integrate information in a way that produces awareness. A galaxy is too large and diffuse to think. The universe is too vast to feel. Consciousness requires boundaries. It requires limitation. Without limits, there's no integration. Without integration, there's no experience. So, being small isn't a disadvantage. It's a requirement for being conscious at all. This reframes the entire feeling of insignificance. You are not significant despite your size. You are significant because of your size. Too small, and the laws of physics dominate. Too large, and coherence dissolves. Life exists in a very narrow, precious window between those extremes. And that window is anything but trivial. It is the rarest of exceptions. There's also a quiet dignity in being part of a universe that doesn't revolve around you. You are not the center, but you are not excluded either. You belong without being privileged. This simple fact removes an immense pressure. Insignificance only feels threatening when we assume that value must be absolute and universal. You matter to the systems you participate in every day, and that value is not diminished by the existence of distant galaxies. The universe doesn't need meaning to function, but conscious beings do. And the universe, in all its vastness, permits us to create it. That isn't a contradiction. It is a beautiful collaboration between blind physical laws and emergent awareness. Smallness is not an obstacle to meaning. It is the very condition that makes meaning possible. Thank you so much for joining me on this thought journey today. See you next time. Once we accept that the universe does not owe us answers, a strange and quiet transformation begins. The question is no longer where the universe ends, or whether it is infinite, or if there are other universes beyond our own. The question becomes something much closer and much more human. How does a small, finite mind live inside a reality that may never fully explain itself? How do we exist meaningfully inside something so vast, indifferent, and unresolved? For most of human history, meaning came from certainty. Ancient civilizations believed the cosmos was ordered around purpose. Gods placed the stars, fate shaped lives. The universe had intention, and humans were part of a story written from above. Meaning flowed downward from the structure of reality itself. But modern cosmology quietly removed that foundation. The universe is not arranged around us. It does not appear to care whether we exist or not. Galaxies form and collide. Stars are born and die. Space expands. Entropy increases. None of this requires us. None of it pauses for us. At first, this realization feels unsettling. If the universe has no built-in purpose, then where does meaning come from? If reality offers no final answers, no cosmic justification, then what grounds our lives? This discomfort is natural. It is the echo of an older worldview fading away. But once the fear settles, something unexpected. Meaning is no longer something discovered, like a hidden law of physics. It is something created, not arbitrarily, but relationally. Meaning emerges from experience, from connection, from attention. Consider scale. The universe is unimaginably large. The observable universe contains trillions of galaxies. Each galaxy contains billions of stars. Each star may host planets. Against this backdrop, a single human life seems negligible. But scale alone does not determine significance. A thought does not need to be large to be real. A feeling does not need cosmic weight to matter. Meaning is not measured in meters or years. It is measured in experience. A sunset does not become less beautiful because it occurs on a small planet. Love does not become less real because it exists briefly. Consciousness does not lose value because it is rare. In fact, rarity often increases value. The fact that awareness emerges at all in a universe governed by blind physical laws is extraordinary. Matter has arranged itself into systems capable of wonder. In this sense, meaning arises not despite the universe's indifference, but because of it. There is no external script telling us what must matter. We are free to decide. This freedom is not chaotic. It is constrained by reality, by biology, by society, by time. But within those constraints, meaning is constructed moment by moment. Living in a universe without answers does not require resignation. It requires orientation. Orientation toward what is present rather than what is promised. Toward experience rather than explanation. Toward care rather than certainty. Science tells us what we are made of. It tells us where we came from. It tells us how the universe behaves. But it does not tell us how to live. That question cannot be outsourced to equations. It must be lived. One response to cosmic uncertainty is despair. If nothing lasts, why try? If the universe ends in heat death, why care? But this response assumes that permanence is a requirement for value. It is not. A song does not need to be infinite to be meaningful. A moment does not need to last forever to matter. In fact, impermanence is often what gives things their intensity. Another response is distraction, to fill the silence with noise, to avoid thinking about vastness by shrinking attention. But this avoids the question rather than answering it. A quieter response is acceptance, not passive acceptance, but grounded acceptance. To recognize that uncertainty is not an error state. It is the default condition of existence. It is the context. Within this context, meaning becomes local. It arises in relationships, in curiosity, in care, in creativity. These are not cosmic answers. They are human ones, and they are sufficient. There is also humility in this perspective. We are not the center. We are not the culmination. We are participants. Temporary configurations of matter and energy, capable of reflection. This humility does not diminish us, it situates us. To live well in such a universe is not to seek final answers, but to cultivate good questions. Questions that deepen attention rather than close it. Questions like, how can I reduce suffering here? How can I understand a little more today? How can I act with integrity in a world that does not guarantee outcomes? Even curiosity itself becomes a form of meaning. The universe may not explain itself fully, but it allows itself to be explored. Every discovery is a conversation with reality. Not all conversations end in agreement. Some end in mystery, but the dialogue itself has value. There is also comfort in knowing that uncertainty is shared. Every conscious being that has ever existed has faced it. Ancient stargazers felt it. Philosophers felt it. Scientists feel it. You are not alone in wondering. Wonder is a collective human inheritance. From a sleep-oriented perspective, this realization is deeply calming. You do not need to solve the universe tonight. You are not behind. There is no final exam. Reality is not waiting for a conclusion. It continues whether or not we understand it. Rest becomes easier when you stop demanding resolution. The universe is allowed to be unfinished. Your understanding is allowed to be incomplete. Peace does not require closure. As we move toward the final parts of this series, the focus shifts again. Having explored knowledge, limits, and meaning, the last step is perspective. Not scientific perspective, but existential perspective. How smallness and vastness coexist. How insignificance and wonder are not opposites, but partners. Thank you for listening, and I hope you'll join me for the next part. At the end of all these questions, after distances too large to imagine and times too long to comprehend, after infinities and horizons and uncertainties, there is a quieter realization waiting underneath everything. The universe does not demand that you understand it completely. It does not ask you to solve its mysteries before you are allowed to rest. It does not require certainty for existence to be valid. Reality simply unfolds, and within that unfolding, rest is allowed. There is a deep tension in the human mind between curiosity and calm. We are driven to ask questions, to push outward, to understand where things begin and where they end. But the same mind that wonders also needs stillness. The same awareness that reaches toward the edge of everything also needs a place to settle. The universe is vast, but you do not need to carry its vastness all at once. When you lie awake at night thinking about infinity, it can feel unsettling. Endless space, endless time, no final answers. But infinity does not press down on you. It does not rush toward you. It does not demand a response. Infinity simply exists, and you exist within it, briefly, gently, without needing to resolve it. One of the quiet truths about the universe is that it does not operate at a human emotional scale. Galaxies do not hurry. Stars do not worry about their futures. The expansion of space does not feel anxiety. And yet, within this emotionally neutral cosmos, beings like us arise, who feel deeply, who care, who fear, who love, who hope. This contrast is not a flaw. It is the point where meaning appears. The universe provides the conditions. Consciousness provides the experience. Neither replaces the other. They coexist. When we speak about the universe having no edge, what we are really confronting is the idea that there is no final frame, no outer wall where everything resolves. But this does not mean there is no ground to stand on. The ground is here, this moment, this breath, this awareness, noticing itself inside a vast context. It is easy to imagine rest as something that comes after understanding, after certainty, after answers. But in reality, rest comes before answers. Rest is what allows thought to soften. It is what allows curiosity to become wonder instead of tension. You do not need to finish the universe tonight. There is something profoundly comforting about the fact that the universe will continue without requiring your vigilance. Stars will form and die, regardless of whether you are watching. Space will expand whether or not you comprehend it. The laws of physics will hold even while you sleep. Nothing essential depends on your awareness being active right now. This does not make you irrelevant. It makes you free. Freedom is often misunderstood as control, but real freedom is release. The release from needing to be central. The release from needing final answers. The release from holding the weight of infinity in a single mind. You are allowed to be local. You are allowed to exist at the scale you were made for. Your nervous system evolved to navigate days and nights, relationships and environments, not cosmic totals. When you feel small beneath the stars, that feeling does not mean you are lost. It means you are correctly oriented. There is a reason ancient cultures connected the night sky with sleep, dreams, and stories. Looking up at the vastness naturally quiets the urge to dominate or resolve. It invites humility, and humility is not humiliation. It is proportion. In proportion, anxiety softens when you realize that no single moment needs to carry the entire universe. Tension loosens. Your thoughts can slow. Your breathing can deepen. The questions do not disappear, but they stop demanding immediate answers. The universe has been unfolding for nearly 14 billion years. It can wait while you rest. Even the unknowns we've discussed are not threats. Dark energy, multiverses, infinities, vacuum, decay, horizons of knowledge. These are descriptions of what we do not yet understand, not alarms signaling danger. Ignorance at a cosmic scale is not failure, it is expected. No species born inside the universe was meant to fully step outside it. And perhaps there is wisdom in that limitation. A universe that could be completely understood might also be completely exhausted. Mystery keeps reality open. It keeps wonder alive. It prevents stagnation. Sleep is a small rehearsal of that openness. When you sleep, you surrender control. You trust that the world will still be there when you wake, that your body will continue breathing, that consciousness will return without effort. This trust mirrors a deeper truth. You do not need to hold reality together. As you drift toward rest, notice how the universe does not rush you. Time expands gently here. Seconds are not counted. Thoughts are allowed to dissolve without conclusion. You are not moving toward an edge. You are settling into a moment that does not require edges. Perhaps the most peaceful way to understand the universe is not as a problem to be solved, but as a context to be inhabited. You are not outside looking in. You are inside, participating. Your existence is not separate from cosmic history. You are one of its expressions. Atoms in your body were forged in ancient stars. Carbon in your cells was created through nuclear fusion billions of years ago. Oxygen was scattered by supernova long before Earth existed. Your body is not foreign to the universe. It is rearranged universe. And your awareness, fragile and fleeting as it may be, is something new the universe did not always have. For most of its history, there was no one to notice it, no one to ask where it ends, no one to wonder. That alone gives this moment quiet significance, not cosmic dominance, not universal purpose, just presence. As this series ends, there is no final answer to hold on to, only a posture, a way of being with uncertainty that does not feel threatening, a way of letting questions exist without tension. Or it may transform. These truths will unfold regardless of what we believe. What matters now is simpler. You are here. You are allowed to rest. Nothing is chasing you. Nothing is collapsing. Let the stars remain distant. Let space stay wide. Let time stretch without urgency. Sleep does not mean disengagement. It means trust. Thank you for joining me on this journey. Until next time, be well and rest easy.